All right, so now let's take a look. Now that we have an idea of what thermochemical equations are, of how we can manipulate them. So if you're manipulating thermochemical equations, and we're going to look at a very couple, maybe simple examples of these here in a second, and then we'll get into some more detail down the road. So the first thing we need to do is we need to specify the physical states of the reactants and the products when we have our chemical equations, thermochemical equations specifically, because they will actually make the enthalpy changes slightly different, okay? So for example, if we look at the formation or the reaction of methane and oxygen to produce CO2 and water. Now, depending on what the physical state of the water is, the enthalpy change for the reaction can be very different, right? So the delta H for this particular reaction, we have water vapor is negative 802.4 kilojoules per mole. However, when we have water in the liquid phase, it's actually positive 89.4 kilojoules per mole. So we want to make sure that we pay close attention to the physical states. Here it's a gas, here's a liquid, when we define or when we use those thermochemical equations. The second thing is due to the fact that we mentioned before that enthalpy is it's an extensive property, so it does depend on the amount of the substance that we have. So for instance, if we have an equation, this first equation here, again, the same equation that we saw previously, that produces or releases 802 kilojoules per mole, which is exothermic, right? So energy released to the environment, to the surroundings. If instead we multiplied all of the coefficients by 2, okay, so now this coefficient here is 1, as understood. 1 times 2 gives me 2. 2 times 2 gives me 4. Right, 1 times 2 gives me 2, and then 2 times 2 gives me 4. So all I did is I took this equation here and I multiplied it by 2, and I ended up with this equation. We also multiply the delta H by 2 as well. Okay, and that's because we have twice as much of everything. So the delta H being extensive, we can multiply that by 2. The other thing we can do with equations is if we have our original equation here, we can reverse the equation. Okay, so now instead of the reactants being on the left and the products on the right, we're just saying we're going to start with this. So this becomes, the products here becomes the reactants, and then the reactants become the products. Okay, so this reaction, in other words, is going in reverse. And if it's going in reverse, we also need to reverse the sign. Okay, so if producing CO2 on H2O releases 802 kilojoules per mole, well then if we use up the CO2 and H2O to make the original reactions, that should require the same amount of energy. So it's the same number, okay? The only difference is the sign changes in both of these, both for the second one compared to the first. Okay, we're going to be manipulating equations a lot when we get to something called Hess's law and the Born-Haber cycle down the road. But for right now, let's just see how we can apply what we know about chemistry, chemical equations in general, and now we're going to tie in some thermochemical data to this. So it says, given the equation for photosynthesis, so this is what happens in green plants. Sugars are made, so this is glucose. Oxygen is released as a result of water and carbon dioxide combining with the help of the sunlight. This process requires, this is endothermic. Okay, delta H is positive. It requires just about 2,800 kilojoules per mole for this to happen. So it requires energy. So it says calculate the solar energy needed to produce 75 grams of C6H12O6. All right, so this here, this value is giving us the delta H as being equal to positive 2,803 kilojoules per mole. And the thing that we're interested in here is the mole of the glucose. Okay, and that is the C6H12O6. I'm just going to write glucose. I don't want to write the whole chemical formula. Now, is the question asking me how much energy is needed to produce 1 mole of glucose? No, it's actually asking me to determine how much energy is needed to produce 75 grams of glucose. So what I need to do and to figure out number of moles of glucose, that's actually here. I'm going to go from grams to moles. Okay, that's something we should know how to do at this point. So we have, we're going to use the molar mass of glucose in order to do this. So I have my 75.0 grams of glucose. Okay, for every 1 mole of glucose, right? I add together the 12 sixes is 72 plus 12 is that 84 plus 96. That's going to give me about 180 grams of glucose for every mole. That's the molar mass. Oh, here it is down. So the grams of glucose go away, and that's going to give me my moles of glucose, which would be 0.416 moles of glucose. And this is where now this part of the thermochemical equation is going to be important, because this is going to be a conversion factor, just like any other conversion factor. And the way that we can relate this is we can say, because the way that it's set up here, right, is it says that we get, or it requires 2,803 kilojoules of energy for every 1 mole of glucose. All right, I just express that as an equality, and then I can turn it into whatever conversion factor I want. Now I want to relate the moles of glucose that we saw before. So I have my 0.416 moles of glucose. I'm going to take that, insert my conversion factor in here, put the units in the right place. I want to end up with kilojoules. So that's going to go on top. I have 2803 kilojoules of energy for every 1 mole of glucose. Moles go away. All right, so multiply that out, we're going to get about 1168, maybe. Let's see, the 3 sig figs, 1170 kilojoules needed. Okay, notice the moles cancel, so it's just a unit of energy, kilojoules, that's needed for this particular process. So my point here is, in addition to knowing how to manipulate these equations, we can use the thermochemical data, the delta H, the enthalpy values, for example, to determine and to calculate the enthalpy change for any amount of something that we have, as long as we have our balanced equation.